Hello everyone, I'm Shreya and today I'm giving a presentation on lattice-based cryptography from the course of Mathematics for Computing. Well, coming to the topic, Introduction to lattice-based cryptography. Before starting to explain this PPT, I need to elaborate the term lattice-based cryptography. Cryptography is a study of the process of encryption, which involves in storing our data and storing it in a private space, not allowing it to be accessed from outside or be hacked. This encrypted data is usually used by many companies such as WhatsApp, and encryption process is used by most of the organizations and websites, etc., to store the data out of the hack, security to security breaches, etc., to keep our data safe. And coming to the lattice-based cryptography is a branch of cryptography that relies on mathematical structure of lattices. So yeah, cryptography is a study of encryption. Mm. So this cryptography uses the mathematical structure of lattices to uh, do the cryptography process. It is it is considered promising candidate for post-quantum cryptography due to its resistance to quantum attacks. Quantum attacks can be referred to miniature attacks, like multiple attacks having a different space or different time at once. Uh, so this lattice-based cryptography is a promising candidate for post-quantum cryptography. This field leverages complex geometric problems to develop some secure cryptographic schemes. So, in this particular field of lattice-based cryptography, we can use complex geometrical problems to develop secure cryptographic schemes, which can store the data using encryption. What is a lattice? A lattice is a regular arrangement of points in n-dimensional space generated by integer combinations of basis vectors. Uh, we have known the concept of lattices since our 8th standard. A lattice is a regular arrangement of points in a crystalline structure according to the physics. Uh, like in a n-dimensional space, like in a or can you give it a place a number in n. The structure of arrangement of how the points are placed represents to the lattice which is being there, like how the points are arranged in a dimensional space. uh, this lattice can be visualized as an infinite grid of extending in multiple dimensions. The how much the number goes, the number of points increases. uh, the lattice also increases in an infinite grid which extends in multiple dimensions. The properties of a lattice are defined by its basis and the geometric relationship between points. Uh, as we study in the at the first year of the engineering, basis are correlating terms which are deeply interrelated to each other. So these the properties are based on the properties of lattice are based on in the basis the geometric relationships between the points which are beside each other in a lattice. Yeah, coming to fundamental problems in lattice cryptography. SVP, shortest vector problem, which involves in finding the shortest non-zero vector in lattice, which is computationally hard. Uh, so how this SVP works is by finding the shortest non-zero vector in a lattice. So a lattice has an n number of uh, points in a dimensional grid. So this SVP involves to find the shortest non-zero vector through which it achieves this lattice cryptography. So to find the shortest non-zero vector, it takes a large amount of computational power, which may distract the main point of the cryptography process. So this lies a fundamental problem in this lattice cryptography process. And CVP, closest vector problem, requires identifying the lattice point closest to a given point. So this also similarly uh, lies in finding a vector which is closest to the lattice a given point. Suppose if a point is taken from a lattice, this CVP requires us to find the uh, a lattice point closest to a difficult point. So there may be a number of points, and the point given to us may be harder to locate it by itself. And to find the shortest point to it, you need to uh, find all the nearest points to it, and you need to find the particular point which is exceptionally close to the given point. So this also requires much computational power and also a difficult part. These problems form the basis for security of lattice-based cryptography systems. So if these problems can be sidetracked or can be solved due to its complexity, the nature of this lattice cryptography process, it may be it may generate very high security for these cryptographic schemes. Coming to the key concepts of this lattice cryptography process, the hardness and security. The security of lattice-based cryptography relies on the computational difficulty of lattice problems. Unlike traditional cryptography, it offers potential security even against quantum computers. The hardness assumptions are well studied and supported by extensive mathematical research. So, what is the main point in this lattice-based cryptography is nowadays the most advanced computers are quantum computers, which are run by using qubits. Uh, these qubits are not like our traditional computers, which use binary code like 0 and 1s, but this qubit can be used to exist in both states at the same time, like 0 1, which provides higher computational capacity and higher computational speeds. uh, Quantum computers can easily use it to can be easily hack using other computers using its very high computational power. But this lattice cryptography, due to its very complex nature and its dimensional structure, it is its main component is a very highly secure structure. So it's very hard to breach it. Uh, so this lattice cryptography, uh, this relies on computational difficulty. Like this process is so difficult that it's very hard to find the very hard to find the like to breach it. So this makes the lattice cryptography hard to breach. Unlike traditional cryptography, which we currently used in most of our devices, it offers potential security even in quantum computers. Like I said before about the qubits and etc. The hardness assumptions are well studied and supported by extensive mathematical research. Even the mathematical research and theory proves that this can be used. This is very highly secure and this is well studied and also supported by traditional extensive research. And yeah, coming to core lattice-based cryptographic schemes. Some of primary schemes include learning with errors (LWE) and ring learning with errors (ring LWE). Like any problem is uh, any problem can be perfected by learning with errors. So what is this pink strategy is due to learning with errors, this can be even more perfected. Uh, Even if, due to its complex nature, but it is due to its highly resistant and highly secure nature. Uh, it is worth it to develop it and integrate it in your lives. So even with learning with errors, uh, we can integrate them in our security systems. These schemes are used to construct encryption, digital signature, and key exchange protocols. This LWE and ring LWE, these schemes are used to construct the encryption, the cryptographic part of the lattice-based cryptography, and the digital signature with which are marks which form when you access the data, and key exchange protocols like the transfer of data among the user and the system. These primary schemes are favored for their efficiency and strong security guarantees. And coming to advantages of lattice cryptography, it provides a foundation of post-quantum secure algorithms resistant to quantum computational threats. So it provides a foundation like the post-quantum secure algorithms, like based on the quantum part of the quantum computers, and threats like quantum computational threats. Lattice-based schemes often feature efficient implementations and good performance. The flexibility of Lattice framework allows for diverse cryptographic applications. Coming to the challenges and limitations, lattice-based schemes tend to require larger key sizes compared to classical cryptography. Most of the cryptographical things they lie behind the secure and do not take up a large amount of data, but these require a large amount of storage due to its very complex nature and the uh, highly secure features. The complexity of lattice problems can lead to computationally intensive operations. Ongoing research aims to optimize schemes for practical deployment and reduce resource requirements. So there are still being improvements done to reduce the requirements and to adjust them in our daily systems. And coming to applications of lattice-based cryptography, secure communication protocols like encryption and digital signature are built using lattice schemes. Uh, so very important, uh, like classified files are stored by using these kinds of encryptions, and to hide the digital signatures, which are built by using these lattice schemes. It supports advanced functionality such as fully homomorphic encryption. Lattice cryptography is also being integrated into blockchain and privacy preserving technologies. Coming to future trends and research, researchers are exploring more efficient algorithms and tighter security reductions. Standardization efforts are underway to establish lattice-based cryptography as a global standard. Continued advancements aim to make these schemes more practical for widespread use. Coming to the conclusion and summary, lattice-based cryptography offers a promising path towards quantum-resistant security solutions. It relies on hard geometric problems, underpins the robustness of these schemes. Ongoing research development are essential to address current challenges and unlock full potential. Uh, so this is how this ends, and this is a very highly advanced field which is being developed day by day. This has a very high scope of being integrated into our lives due to its very special nature and its highly useful capabilities. Uh, so thank you for listening to the presentation. Uh, this is my presentation. Thank you.